Hi, in the second lecture of producing biomethanol from biomass, where we are doing process synthesis, we are going to be looking at using the water gas shift reaction to correct our H2 to CO ratio, as we have discussed in the first lecture, lecture 1, where we were doing gasification of the biomass to produce the synthesis gas. The layout of the lesson is we are going to look at the water gas shift reaction equilibrium. Remember, from the problem statement, we have been told that we have to use equilibrium reactor to simulate the water gas shift reaction. And then once we have looked at the equilibrium of the water gas shift reaction, we are going to see how we implement that in ChemCat, doing the simulation of the reactor. And then we are going to review options that are available in the industry for cleaning up the synthesis gas once we have produced it. If you remember from lesson 1 that in this particular setup that we have, where we are gasifying sucrose, we are producing the H2CO ratio of 3.18, which is much higher than the one that we require for methanol synthesis, which is 2 H2s for 1 CO, which meaning that the H2 to CO ratio of 2 is required. We can look at this to use the water gas shift reaction to produce more CO and reduce the H2, and also use some of the carbon dioxide that we have produced in the gasifier, which means that in its usually a conventional direction of the water gas shift reaction, we are going to look at the reverse, which is this one on the side here. So we are going to be looking at using that excess hydrogen that we have. Instead of having 2, we're having 3.18 for each mole of CO. So we are going to have to use up that excess 1.18 hydrogen, which is not exactly the true story, but whatever excess that we have to use it up to make more CO. The advantage of that is, remember, we have CO2 in our syngas produced from the gasifier. The advantage of this is we will also use up CO2 to make CO. Remember, CO2 is basically, it becomes a waste of our carbon that we are feeding into the system. So if we use it up to making CO that we can use to make methanol, is actually a very good step to take in the situation. The water gas shift reactor is the second in our sequence, or in our block flow diagram. And then remember, the way the reaction is going to occur is in the direction of using up CO2 and H2 to producing CO and water. So what this essentially means is that there will be no water feed to the water gas shift reaction, because we don't need water in the reaction. However, we just need to emphasize that this reaction is going to produce water. So you will need to remove water somewhere downstream. I'm not saying it has to happen after methanol synthesis. I'm saying it has to happen somewhere downstream. You may opt to remove it here. You may opt to remove it here. Somewhere downstream, you're going to have to remove that water. But as we continue to build this flow sheet, you will see that we will have to assess those decisions as we carry on. The water gas shift reaction is a reversible reaction, usually given in the conventional direction of carbon monoxide reacting with water to form carbon dioxide and hydrogen. And as we have stated, in our situation, we would like it to go in the opposite direction. Remember, it's a reversible reaction. It doesn't mean that it's happening in one direction. All we are saying is the conventional format that is usually presented in is water and CO going to form the gases. It is reversible, meaning that the reaction goes in both directions. Both hydrogen, this side, and carbon monoxide, this side, gets produced. The reaction is a constant volume reaction. It is an equal, which means that it's an equimolar reaction, that the equal amounts, molar amounts of reactants and products get formed. So you are reacting 2 moles, 1 mole to form 2 moles, 1 mole, 1 mole. Therefore, the equilibrium of this reaction is not influenced by the change in pressure or the change in volume, because equal number of moles get consumed as compared to the same number of moles getting produced. Generally, for reversible chemical reactions, an equilibrium constant is introduced, which basically means that is the ratio of the reaction rate in the forward direction and that of the reverse direction. So the equilibrium constant is usually given as the ratio of products over the ratio of reactants. So where the ratios are molar amounts or partial pressures or volumetric fractions, depending on how it is expressed in the equilibrium constant that you are using. In this situation, equilibrium constant will not have any units because of the equimolar distribution. If the concentration of CO has units, it will and that of water has units, they will cancel with the ones below. Okay, the equilibrium constant for the isolated reaction of water gas shift, meaning that if it occurs alone without the interaction of other reactions, can be empirically expressed by Twigg in that catalyst book by Twigg, which was published in 1989, as the following expression, where it's basically an exponential of temperature, an exponential function of temperature. Here we are using Z, but Z basically is a function of temperature. If we plot that equilibrium function, the Kp, as a function of temperature, we can see that it is decreasing with temperature. This, if you look at it, it essentially means that hydrogen production is favored at lower temperatures because of the fact that at lower temperatures the Kp is increasing. So at lower temperatures, if the Kc is increasing, it means that the products are increasing. And then CO production is favored by higher temperatures, because at higher temperatures the value of Kp is much lower compared to at lower temperatures. So the denominator becomes bigger. That's what it essentially means. Okay. Carbon monoxide production is favored by high temperature, as we have stated. And remember, we are aiming to produce carbon monoxide. That's our direction of the water gas shift reaction that we are looking at. What you can do is we can solve the Kp equation to give us the molar ratio of 2. We know that Kp, if you look at this equation, Kp is equals to this, which is a function of temperature, and equate it to the molar ratios that we are targeting, and then you can solve for temperature in that end. But solving for temperature for this expression would become a little bit tedious. You may have to use trial and error. You may try to do it in Excel, but most of the solvers will struggle with the solution. So what we are going to do is we are going to use trial and error in ChemCAD. We are going to put up a simulation, and then we are going to play with temperature until we get the molar ratio of H2 to CO being equal to 2. So that's what we will do here. We will put up a simulation with as we have. We'll continue. Remember, we have a simulation up to here where we have the gas coming out of the gasifier. Now what we'll need to do is just put the water gas shift and keep playing around with the temperature here until it gives us the H2CA ratio of 2 as we are targeting. Okay, we have started to implement that water gas shift reaction in ChemCAD. What I have done is I've just included that reactor here, which, as you know, it comes from reactor, and it's equilibrium reactor, which is this reactor here. All I've done is just rotated it in such a way that it's laying horizontal, because I wanted as much space as possible for my flow sheet. And then I have also added a separator here just to separate the components. We will not be looking into this yet at this point. What we are going to be looking at is just the water gas shift reaction. So once we have connected that, you can go into editing your reactor. We are, because of the fact that we are lucky that if you look at the specify reactor type on ChemCAD, it says general equilibrium reactor. You click on that, you have the shift reactor and the methanation reactor. So ChemCAD has those two built-in reactors because they are usually in petrochemical and chemical engineering. They are used quite frequently. So we will just select the shift reactor. Once we have selected that, the ChemCAD will know exactly what's happening. It is the water gas shift reactor. Then the next step that we'll do is let's go isothermal on the reactor so that we keep the temperature of the reactor constant. So we can start with whichever temperature we'll start with. So let's say we'll start with a temperature of 300 degrees Celsius. And then to specify the calculation mode. This essentially, it just says that you can specify a couple of things. You can specify the reaction conversion. You can specify the approach delta T or the approach fraction. This comes from the fact that reactions never actually get to equilibrium, because as you get closer to equilibrium, the rate of reactions becomes slower and slower. So the calculations become more and more complicated. So, and it takes longer and longer time. So what this says is how close you want to be towards equilibrium. So I always say I just want to be 10 degrees away from equilibrium instead of calculating equilibrium at 300. You know your equilibrium is at 300, but you are doing the calculations at 290 or at 310. That's how close you have to be to equilibrium, so that the calculation does not become the accuracy that you require. It becomes a little bit rough, but your calculations become faster, and your conversion of the calculations become easier as well. Okay, that's all you need to know. If you look at the more specifications, this side we will not be looking at the accuracy of the calculations. The reaction engineering units, you will see this will come into play later when we do the kinetic reactor. At this point, because of the equilibrium reactor, we don't have any more specifications that will require us to specify the units. But all I can say is you can always say temperature is in degrees, but we will not be using that. This usually works well when you are specifying more constants within the reactor. So this side, just leave it as it is. Do not tamper with it. Going back to the general specification, the liquid, our reaction is vapor only, so we will not have to worry about the liquid equilibrium constant. So we are in the vapor only. We will be operating at higher temperatures. So the assumption is even the water will be in its vapor phase, as this reaction occurs only in the vapor phase. So you have to specify the vapor phase. Okay, I'll leave specify the initial temperature as 300, and then I close the simulation, and then we can run the simulation and see what comes out. Then what you would essentially do here is you would come and look at your H2 to CO ratio. As you can see, our carbon monoxide is 6, our hydrogen is 17. This is still way above 2, because if it was 2, our hydrogen was just supposed to be around 12 point something, 12.4, because there we have 6.2. So which means that in our direction, remember we said we are going to be producing CO2, and CO2 is favored by slightly higher temperature. So let's increase the temperature because we want to be using up hydrogen. Remember the direction of the water gas shift that we were dealing with, it is favored by higher temperature. So let's increase the temperature further. I would say let's go to 450. I would usually go higher so that I pass the required point and then select maybe a point in between, but at this point I will just go sequential and say let me go 450, and then let's run this, and then we can look at this. We have increased our carbon monoxide slightly, but our hydrogen is still the ratio is supposed to be, if you look at it, 7.3, maybe supposed to be 14.6 for hydrogen to be right on the molar ratio of 2H2 to C ratio. So we still need to ramp up a temperature a little bit. You can keep doing this until you fine tune it, but since I've done it before, I know that my temperature that I'll be looking for, I think, is 503. I will have to check that first. Let's run this and then we can quickly check this. Okay, we are closely getting there. I mean, it's almost 8 and then we have 16. So you can fine tune it until you get the exact number of the ratio of hydrogen to carbon monoxide being exactly 2 or slightly above 2. I would say just slightly above 2 would be okay. Don't go below, because then you'll have excess carbon monoxide, which I would not really want to end up with carbon monoxide in my reaction stream. I'd rather prefer to end up with excess hydrogen in my stream. But you don't have to worry about fine-tuning it to be exactly 2. Just get it slightly above 2, that will be fine. Because again, remember, the methanol synthesis reactor is not going to be a 100% conventional reactor. It's going to be a kinetic reactor, which means that it will have a specific conversion type to it. In industry, I know it is usually around 20-25% per reactor, the conversion that you get for methanol synthesis. So you will still have a lot of gases that you have to recycle. So you just have to tune it to be very close to 2. You can always come back to it, because with the recycle coming up, this ratio will keep changing, and then you'll have to come and fine-tune this flow sheet going forward. Please note that as the flow sheet as it is, it's not representative of what you are going to produce as a flow sheet. We are deciding on the temperature in the reactor here. If the temperature coming out of the gasifier is higher, which as you can see it is higher, it's 1150 degrees Celsius, and here we are saying we are just around 500 something degrees Celsius, which means that you will need a heat exchanger here to reduce that temperature. I would need to see that in your flow sheet that you produce. That heat exchanger is going to use cooling water. I would need to see the flows of the cooling water, the flows of the utilities. That's what your flow sheet needs to look like. This one, I'm just guiding you through the flow sheet synthesis. For your flow sheet, you need to specify everything. If the pressure needs to increase, I need to see a compressor. If the pressure needs to reduce, I need to see an expander, a valve. If you're feeding steam, I need to see where the steam comes from. Usually you are given water, steam is not available on site. I need to see you boiling the water to forming steam that you're going to feed into your system. If you have a distillation column, I need to know what you're going to heat the bottoms with. I need to know what you're going to cool the condenser with. So all those need to show in your final flow sheet. I need to see the process streams. I need to see the utilities as well. Okay, thank you. Then let's move back to our presentation slides, since we have done the simulation in the situation. Okay, from our trial and error in ChemCAD, we end up with a temperature of 530 degrees Celsius, giving us this flows of H2 to that flow of CO with a ratio of just around 2.01, which I said I'm okay with. So your situation will be different, since you have a different feed stream coming from a different biomass that you are given. So your temperature, tune it to get to where you need it to be, just around 2 will be fine. It will be interesting to come back after we have done this calculation and look at the financials on how this decision improves or worsens the economics, because remember, we have added an extra reactor, which is the water gas shift reactor, and then that helps us to improve the amount of methanol that is made, and then also to use the H2 that we had. It will be very interesting to come back and look at how this additional reactor improves the amount of methanol that we make, and then also that additional methanol produced, how does it offset the cost of the water gas shift reactor and its accessories. As you know, it will have the water separation unit. We did not have water, now we have water into the system. We will need to cool after the gasifier because the temperature is slightly lower, and then also there will be other utilities, other accessories, other auxiliary equipment that you will add just because you now have the water gas shift. It will be interesting to come back and then assess this to check if it was worth it to do this shift. I would say for the CO2 footprint, because we are using quite a bit of CO2 to make carbon monoxide, which we are going to use to make methanol. From the CO2 footprint, it does make sense because we are always trying to reduce the CO2 footprint. Okay, after the water gas shift, now our synthesis gas is ready for methanol synthesis, or is it not? If you look at our stream, we have 7 mole of water, we have 13 mole percent, we have 7 mole percent of water, we have 13 mole percent of carbon dioxide. These two components are not required for the methanol synthesis. So we need to start thinking about what we are going to do. Should we separate this? Should we remove water and carbon dioxide? before methanol synthesis. If we don't choose to do that, which means that our reactor will need to have 20% more capacity. Actually, it's 25%, because if you look at it from the inverse, it would have been 80% smaller. So if you make it 100%, so it's 25% more. So if we choose to separate them later, it will mean that methanol reactor will be oversized to accommodate these unnecessary components. The reactor will have to be at least 25% unnecessarily bigger. Also, the compressor will have to compress these compounds from 20 bar. Remember, our gas from the gasifier comes at 20 bar, and then we'll use the water gas shift at 20 bar as well. We'll not change that. Then to compress these gases, these 20% extra gases, we will need to oversize our compressor. We'll need to waste the energy on compressing them before we separate them. So also we may need to do distillation to separate methanol and water, because now after producing methanol, we will now have a binary mixture of methanol and water, which we would not need if we do not have water in the system, because it will just be an easy separation of methanol from the gases. So all these decisions, you need to think about them. So I would say my decision here, it would be to avoid distillation downstream. I need to remove the water. I'll need to remove it. Separation of these gases and water will be just cooling down to a lower temperature where water will condense, and then I'll separate the water. And then what do I do with the CO2? Do I let it go through the methanol synthesis reactor, or do I separate it right now? All these decisions, you need to consider them before, while you are doing your process synthesis, and you need to justify them every step of the way. And then in your process description, you need to state why is your process that way. In your process synthesis methodology, you need to state why you decided to do all this. This is in the end, your document, your report will capture all these decisions. Why is your process synthesized the way it is? For this design, at this point, I will choose to remove the water and CO2 at this point. As we have stated, the removal of water from gases, it will be simple. It will be a simple flash separator. We will need to condense the water by cooling. That's not too complicated. Or you could choose to increase the pressure, because higher pressure also will condense the water, but I think cooling will be a better option. We will also need to remove the CO2. How will we remove the CO2? CO2 removal usually occurs in the processes that are referred to as acid gas removal in the industry. They are called AGRs. The most common technologies for acid gas removal are cyclic, regenerable, solvent absorption processes. We will just quickly briefly look at those, just to give you an indication of what these technologies are. Removal of water, cooling, and a flash separator. That's easy. But now you are left with gases that has CO2. You have CO2, hydrogen. Now you need to remove CO2. The AGR processes, you have a liquid solvent that is countercurrently contacted with SYNGAS in an absorption tower to selectively remove hydrogen sulfide and or CO2. Usually the acid gases in the synthesis gas always, in most cases, it does include hydrogen sulfide. Once the solvent has extracted these acid gases, it is then thermally regenerated by stripping it in a stripping tower to liberate the acid gases, while rejuvenating the solvent to begin the absorption cycle again. There are three generic types of acid gas removal based on the solvent used to remove CO2. At the top of it, we have the chemical solvents, which usually use MEA and MDEA solvents. This chemical solvents are aqueous bases that undergo reversible acid-base reaction with the acid gases after they hydrolyze in water to weak acids. The absorption process typically operate at room temperature. As the examples of those are using MEA and then MDEA. Typical simulation of MEA on ChemCat looks like this. As you can see, it's not a very simple simulation. It has pumps, compressors, heat exchangers. So this would be a type of simulation you would do just to remove the CO2. Using MDEA, as you can see, the trend is slightly the same. That you absorb and then you regenerate. On this side, you absorb the CO2, and then once you have absorbed the CO2 into the solvent, you come and regenerate the solvent and then recycle back to the absorber. The second class of AGR uses physical solvents. The physical solvents that have usually have positive and negatively charged portions that attract the polar acid gases, which are H2S and CO2. And the absorption process typically operate at low temperatures and may require refrigeration. This is this type of physical solvent application for AGR is very popular. The process that usually used are they use solvents such as Selexol, Rectisol, Pyrisol, and Morphisol. These are usually the name of this are based on the proprietary solvents that is used to absorb the acid gas. The next is the combination of the physical and the chemical, which is combination of 1 and 2. This one uses a mixture, a solvent that has a mixed properties that exhibit the mixture of properties which combine the features of the first two types. Cooling and refrigeration may also be required here. The examples of these processes are sulfinol and amisol. These are based on the solvents, the proprietary solvents that are developed by the technology licensors or providers of these type of AGR technologies.